or technique that we use with certain kinds of functions. So last time we talked, I mentioned that it's really important that we look at a function and how it's sort of created or put together from pieces that we already know. So we see this is like the cosine of 8x, which is a function we should have a little experience with. And then also it's raised to the x power. And so it turns out that this function is of the form f of x to the g of x. So it's one function of x raised to another function of x. That one, of course, is just x, but it could be square root of x or any kind of function of x. And when you have this particular form, this tells us we need to use logarithmic differentiation. It's not like our other kinds of functions that we already know. So some other functions that you would have seen before, x to the n, this is just a regular power function, right? That's nx to the n minus 1. F of x to the n. So if n is a constant here, this is also like a power function. This is a chain rule problem. This is going to be n f of x to the n minus 1 times f prime of x. So that's the chain rule. That's from 3.4. I'll talk a little bit more about that, but this is also a sort of previously known rule. This one is not this. It doesn't apply because the exponent here is just a constant. This exponent is a variable. So it turns out that's a different kind of function. You may also remember a to the x. So this is an exponential function. We've done e to the x before, right? But a to the x is very similar. It's a to the x times the natural log of a. So this, what I'm doing here, right? This side is my function f of x. And this is my derivative of that function f prime of x. But again, this type of function is not that. This has a constant base and a variable exponent. So that's not this. So we have to use a different technique here, which is called logarithmic differentiation. And in order to use logarithmic differentiation, I need to give you, a couple tools. Logarithm is a new kind of function. So the derivative of the natural log of x, it turns out, is 1 over x. You can show this derivative by sort of a couple different tools. And often we're going to use absolute values there. That makes the logarithm more versatile when you sort of define it using absolute values, because then it can hold for positive or negative values of x. You can still evaluate it. So we could illustrate this derivative a little bit by a graph. We could also show it using implicit differentiation, and I certainly do that in the lecture. So if you watch the lecture over this section, I do implicit differentiation to prove that. Or you can also just trust me, right, in the book and say, okay, I guess that is the derivative. I don't really like that trust me. It makes me kind of nervous, right, that you just sort of trust what someone says without having any information about why that's actually true. Let's just look at the natural log of x. This is the natural log function of the absolute value of x. And that's easier to trust me because you just plot points. You just put in different values of x and you get this kind of curve. And 1 over x looks like that. So let's just take a quick second to think about, does the red derivative match up with the blue original function? And I do that by thinking about tangent lines. And what I see is that every tangent line here is negative because the slope is going down, sorry, the slope of the tangent line. And notice all of the y values for the red function are all negative. So that's good. These slopes are very flat, close to 0, and the red function is very close to 0. On this other half, here all of the slopes are positive, and notice the y values here are all positive at every point. The slopes here are getting flatter and flatter and closer to 0, and notice the y values here are getting closer and closer to 0. So visually, this is no proof, but visually it certainly seems plausible that 1 over x is the derivative of the natural log of x. There's nothing here to say it couldn't be. And what we like to do is remember these rules rather than just natural log of x. It's more versatile if we can imagine this inner function to be anything. U, that was a bad U, right? That looks like a scribble now. Where this is any function of x. This is the chain rule, and it's where functions are nested inside one another, right? We talked about product rule and quotient rule. The chain rule is where you have an inner and an outer function. And the rule for derivatives of natural logarithms are du over u. Okay, so that's the chain rule. It's 1 over u, right? The derivative of the outer function, 1 over x, evaluated at u. So I put u in for x, and then I multiply by the derivative of whatever u is. So I promise I'll get back to this question, but let's let f of x equal the natural log of x squared plus cosine of x. So the derivative here, this is exactly the situation. I have the natural log of some function. Excuse me. The derivative then is the derivative of u, right? This is functioning as my u. So the derivative of u is 2x, and then the derivative of cosine is minus sine. So that's my du, and then the bottom is just exactly u, x squared plus cosine of x. So as our rules go, logarithms are actually pretty good, right? They're kind of easier in a way than products or quotients. I don't have all these different parts that I'm adding and subtracting. I just have a top and a bottom, du over u. Okay, so, and you know, with these derivative rules, there is always a reason for them and a sort of proof of them, but at the same time, you can do fine by just following the rule. This is a little bit of a procedural type of problem, right, with taking these derivatives. You really need to do the procedure to get the correct derivative. So, it's nice to kind of understand where the rules come from, but it doesn't really help you when you're actually finding the derivatives, right? So it's like, I know where the rules come from, but I'm not really thinking of the rule at all when I take the derivative. I'm just following this pattern and this structure from the formula. Maybe one more example. How about the natural log of tangent of x times the square root of x? Let's that be my function. So when you're going to find the derivative, you've got to take a second to look at the structure. Like, okay, I know tangent and I know natural log and I know square root, but how are they put together, right? That's going to determine what rule and what sort of strategy I'm going to use for finding that derivative. So what I see when I look at this is I have the natural log of the tangent. That to me looks exactly like this pattern, but this is really one function times another function. So this is going to be a product rule first and foremost. I'm going to take the derivative of the first, which is this, and if you're feeling comfortable, you can just go ahead and take that derivative right away. If you're really uncomfortable, you might want to write that down. Derivative times the other plus the derivative of the other function times the first function. So the derivative of this is the derivative of tangent, which is secant squared, divided by tangent. This is my du over u pattern, times the square root of x, plus the derivative of my second function. The derivative of the square root is 1 over 2 square roots, times my original function, natural log of the tangent of x. So this natural log function can be multiplied and divided and added, all those other combinations. We need to mix it in with our other rules. Okay, any questions about either of those two examples? Like I said, it is actually really a nicer rule than certainly the quotient rule and probably even the product rule. So it's not something to shy away from, but it is a different structure than we're used to, right? This du over u. Okay, so how does all of this apply to our original problem? Cosine of 8x to the x. There's no logarithms in there, right? So why would we use logarithmic differentiation? The reason is that logarithms have some very nice properties when coupled with derivatives. And let me just remind you of those from college algebra. The logarithm, it doesn't matter what the base is, of x times y is the logarithm base a of x plus the log base a of y. This is nice actually, because remember when you're trying to take the derivative of a product, it's a little complicated, but a sum is much easier. So a logarithm actually takes a sort of slightly more complicated situation and turns it into a really easier situation for us. And it does that with products. It also does that with quotients. And most importantly for our scenario, it also does that with powers. The natural log of a, base a of x to the r is r times the log base a of x. And a lot of times we think of that rule as taking this exponent and pulling it out in front as a multiplier. Multipliers are easier than exponents for us to deal with typically. So that rule there, that third one that I'm listed, that's what's going to help us deal with this unusual form, right? Remember I said in the beginning, if you have a function raised to another function, that needs logarithmic differentiation. I can't actually deal with this form directly. I need to get this exponent turned into a multiplier. And so the way to do that here is to introduce a logarithm to the problem. And the logarithm we've been working with, and the easiest one to work with, is the natural logarithm. So what I'm going to do is I'm going to take the natural log of both sides. That's an algebraic step, and we can do that. This rule tells me this exponent can then be pulled into the front. And now I don't have any powers to work with. I just have to take the derivative here. Now, in order to take this derivative, we need to use implicit differentiation. And that is 3.5, implicit differentiation. So this one problem here gives us a lot of opportunities to do a little review and look at things. Implicit differentiation is when we take the derivative of something that is not exactly written as a function of x. So what we're implying here is that y equals some function of x, but it's not written clearly what y is, or explicitly what y is. It's sort of implied. And when we take implicit differentiation, when we take the derivative of an implicit function, anytime we take the derivative of a y, we're going to also get its derivative, y prime. And that's the chain rule. And I've had a couple people ask questions about that in the last couple days, and for good reason. It is a little, well, we could say confusing, right? Where and how that part comes from. On the other hand, I do think it's not, it's very reasonable to do it. In other words, you can do it even if it doesn't totally make sense to you at this point. And unfortunately, that's the way some calculus rules and structures work, is that it's hard to explain them without sort of doing them first for a while. Seems counterintuitive, but I think that's actually kind of normal. I don't think you could like coach someone on golfing advanced golf techniques if they'd never golfed before, right? They have to kind of work through some things for a little bit before you can refine your approach. So when I'm taking the derivative of natural log of y, because it's not y equals, it's natural log of y, when I take that derivative, I have to use my same logarithmic rule here, du over u, because y is some function of x. So the derivative of y, we're calling y prime. This is my du over u, or dy over y. Right? That's what the chain rule says is the derivative. When I take the derivative of the right side, this is a product rule. I have x times this natural log function. So the derivative of the first times the second plus the derivative of the second. So my second function is this, right? The derivative of the natural log of the cosine of 8x. I take du over u. Remember, since it's the cosine of 8x, the derivative there is minus sine of 8x times 8. That's the chain rule again. So this is the derivative of natural log function, and then I multiply that by x. I wish I was in class, right, to see your expressions. But my guess is that some of you are feeling a little maybe blown away by parts of this. That's okay for right now. But these are all some parts that we want to be getting more comfortable with, right? So start to see the structure. We're actually in really good shape here. It looks bad, but we're really close to finding out what y prime is. I just have to multiply both sides by y. I get the natural log of the cosine of 8x plus, let's make that minus 8x sine of 8x over cosine of 8x. And then the very last thing is just to say, well, I don't want my derivative written with y values. It should be with x if possible. And so I'm going to replace that y with this, with what y is, cosine of 8x to the x. So instead of y here, I'm going to replace that with the cosine of 8x to the x. That's a logarithmic differentiation example. It's probably the hardest kind of derivative that we'll see and have seen, at least, yeah, probably. It involves, there are easier versions of logarithmic differentiation, but this one involves the chain rule as well. So that's maybe what makes parts of it look a little bit more complicated. Are there questions on any of these steps? Did I scare you all off? Are you dismayed? I hope not. Are there any other questions from the homework that you'd like to see me go over? So the chat's not coming up for me here. Yeah, yeah, Caitlin, I think that's exactly, that's the hope here, right? Is to say like, okay, I'm not positive I'd be able to do all of those steps right now, but the overall flow of the problem is really what I'm hoping we start to pick up on, and then we can fill in those individual steps. Like I said, to do this problem, you need implicit differentiation, you need product rule, you need chain rule, you need basically all of our tools that we're probably still working through a little bit. And again, this is like, I think the last problem from 3.6. So we've got a little bit of time to keep working to get to there. It doesn't seem, I'm not seeing any other questions. So let me just run through a couple hopefully more straightforward examples. Of both the chain rule and a little bit on implicit differentiation. In many ways, I think the chain rule is perhaps the most important of our rules. We use it a lot. So just to remind you, the derivative of f of g of x. So this is where you have a nested function, right? This is f prime of g of x times g prime of x. So you take the derivative of the structure of the outside function, you plug that inside function in there, and then you multiply by its derivative. So for example, if y equals the sine of e to the x, this is a nested function in this same structure. The sine function is the outside or the f, and the e to the x is the inside or the g. So this rule tells me exactly how I should take its derivative. I should take the derivative of the outside or the sine function. That's what this f prime is. The derivative of sine is cosine. And then instead of having cosine of x, this says I'm replacing x with whatever that inside function is, e to the x. And then the rule says I multiply by the derivative of that inside function. The derivative of e to the x is e to the x. It is very, very important that you distinguish between this function and this function, right? They both involve e to the x and sort of a sine of x, but they have a very different structure, right? This is a product rule, just a product of two functions. So its derivative would be the derivative of the first times the second plus the derivative of the second times the first. Very different derivative, very different structure to the problem, even though the two functions are of course very similar. So that's another example, right, of really looking at how the functions are put together. One type of problem that often gives students some trouble is like this kind of thing. This cubed, when it's written here, really means the tangent of the natural log of x cubed. Right? And I think for a lot of students, it's easier or easiest to actually write that out so that you can see the structure a little more clearly. The outside function here is a cube function. So its derivative is going to be 3 the function squared, right? Following my same chain rule. Instead of x, I'm putting g of x, right? And g of x is my inner function, which is tangent of the natural log of x. And then I multiply by the derivative of whatever that inner function is. Think of this one's like peeling an onion. I've got like, I peeled off kind of the outer function and now I get to see what's inside. What's inside is tangent of natural log of x. So this is another chain rule situation. The derivative of this, I have to use the chain rule. The derivative of tangent is secant squared. I replace the x with the natural log of x. That inner function doesn't change. And then I multiply by the derivative of the inner function. Right? Luckily here I'm done, right? I've peeled off the last layer. I know the derivative of the natural log of x because we just talked about it. It's 1 over x. Right? There's no chain rule there. That's a function I know the derivative of directly. So one nice thing about the chain rule is there's usually not any simplification that you need to do because it's often written as a product already, just like this one is. Okay. Questions about that problem at all? You're all very quiet today. Was it, I don't know, missing last week? Did that throw off our relationship, our groove? I hope not. Questions are a good way for me to see where you're at and to help you. So I really appreciate and I like answering questions in some ways better than lecturing, because when I'm lecturing, I'm never sure, like, is that useful? Is that not useful? At least when it's a question, I know that I'm addressing something that is important to you. Okay, so those are a couple examples from the chain rule. Again, you should have already completed that homework assignment, but it's never a bad idea to see a couple more examples of chain rule problems. The other strategy we used in that logarithmic differentiation problem was this implicit differentiation, which is 3.5. That's the one that was due yesterday, but is you can continue to work on that penalty-free through today. Implicit differentiation is where we think of the y as being some unknown function of x. A lot of times we know what y is, like this example right here, right? Y is the sine of e to the x. That's written explicitly. It tells me exactly what y is in terms of x. And normally when we sort of take the derivative, we don't really think of the y value, but you really could think of just taking the derivative here of both sides. That's normally what we do with equations, right? Is we do the same thing to both sides. So if I take the derivative of y, well, that's exactly y prime, right? That's really what we call the derivative of y. And then the derivative of this side, we use our rules. But when you have an implicit function, it's not always clear exactly what the y is. So for example, y cubed plus y times the cosine of x equals x to the 5th. So like this one, the y is all mixed up with the x. I actually don't know how to write y in terms of x. This may not even be really solvable for y. It kind of is because it's a cubic, but it's really hard and really messy. So it's not something we're able to rearrange, but we can still think of it as a function of x, even if it doesn't fit our normal sort of function rules. So this very likely doesn't qualify as a standard function where each input has a single output, because it's a cubic function in y. It probably has at least a couple y values for certain x values, but we can still find its derivative and interpret its derivative by taking it implicitly. So here, when I take the derivative, I'm really just thinking of taking the derivative of both sides. And as I mentioned in the previous, that kind of long logarithmic problem, every time I take the derivative of a y value, I have to use the chain rule. So the derivative of y cubed, remember y is some function of x, like cosine or sine, or it's not, right? Because that wouldn't actually work here, but it's something like this. And if you had something like that cubed, your derivative would be 3 times that something squared times the derivative of that something. That's the chain rule. And of course, the derivative of y is y prime. So every time I take the derivative of y, I'm going to get this y prime. Here, this is a function of x, y times cosine of x. So that's got to be a product rule. The derivative of y is y prime. The derivative of cosine is minus sine. I don't have y prime here because I didn't take the derivative of y in that second half. I just took the derivative of cosine and multiplied it by y. And then finally the derivative of x to the fifth, right, we know is 5x to the fourth. So when we do this, we keep or maintain equality, assuming we take those derivatives correctly. And this then gives us an equation involving y prime, which is what I want to discover, right? That's my goal, is to find the derivative. So here there are two terms that have a y prime, so I can factor the y prime out of those terms. And I'm going to move this term that doesn't have a y prime over to the other side. And it's just algebra here. I divide both sides to get an expression for y prime. I'd probably write that y times sine of x. And this is the derivative. Remember, the derivative gives us the slope of the tangent line at any point. So if I want to know the slope of the tangent line here, I have to plug in an x value and a y value to figure out exactly the derivative. And that's because this function, just knowing the x value isn't enough. If your function, looks like this, right? Not a function in our standard sense. If I just tell you the x value here, well, you don't know which point I'm talking about, and all those points have different slopes. So in order to actually figure out what the slope is for this equation, I'm going to need to plug in both an x and a y value. So I need to tell you actually, oh, it's at this point I'm interested in the slope. If you know that x and y, and you plug it in here, it will create a value for y prime. That value will be this slope of that tangent line. Your lab is about implicit differentiation. You have sort of a very complicated function to work with, but luckily you can have Maple do all the heavy lifting, right? Solving and things like that. And there's some instructions how to use it to solve. But you have to give it the right things to solve, right? You can't just say solve the problem. You got to say, find this equation or whatever it might be. Are there questions at all about that example? Questions? Okay. I hope that's a good sign. I was expecting to be deluged with questions, but we weren't. So we can sort of wrap this up here. I would really encourage you all to come on Thursday as well. Since we're getting closer to the midterm, there's a little less time to catch up, right? If some ideas are a little slow in coming. I'll spend some more time over 3.6 working with these logarithms, and I will also introduce 3.9, which is a kind of applications problem, some called related rates. And we'll want to see some of those examples too. I'll also make sure to have all the review material sort of posted and ready by Thursday. And we can talk about whatever other questions you might have. Okay.